Okay, let's get started. Okay, welcome to week 5 of Computational Systems Biology. My name is Shomo. I'm the PMRFTA for this course. So, in the last weeks, we discussed about different types of biological networks, gene regulatory networks, protein-protein interaction networks, metabolic networks, and how you can construct these networks using already available data and how you can generate hypotheses uh, using analysis of these networks and a few specialized algorithms like Galois-Newman algorithm on how you can detect communities within a network and so on. So today's focus is a little bit different to what we have been studying for the last 4 weeks. This is more on the analysis side of how you can analyze these different biological systems using mathematical models, primarily through the use of differential equations, and how you can kind of say generate hypothesis and test your hypothesis uh, using this kind of techniques. So, just a quick overview. This slide I've kept the topic as modeling in systems biology. So basically, this is a comprehensive kind of pipeline, you can say, to how different analysis of different modeling is done in systems biology experiments. So you have a prior knowledge of components, interaction, and pathways or networks, either from known literature using wet lab techniques or in silico experiments with sufficient amount of evidence. Then you specify a pathway or a network topology, and you develop equations describing the interactions between these different pathways or network topologies. Then comes the analysis part or the mathematical part where you parameterize equations with initial concentrations, chemical rates. You have comprehensive parameter sensitivity analysis for identification of which parameter works best for this particular equation, and you kind of do this iteratively to find the best fit equation which best describes your model. So uh, the models that we'll be talking about are primarily chemical kinetics-based models. So you have reactions and intermediates and enzymes involved in those reactions, and we'll model these as a continuous set of variables that kind of start with a particular substrate and end with a particular product. And that product again is used up as a substrate in a separate pathway or a separate module. So this whole continuum thing is kind of modeled using differential equations, and the parameters of these equations are something of very importance, because depending on the parameters your the behavior of the systems changes. So identifying the parameter and estimating the parameter is very important, and we'll talk a little bit on parameter estimation techniques as well. Okay, so I hope everyone is familiar with at least the basic stuff of ODE. What is an ODE? So the full form is ordinary differential equations. So it's basically an equation with a dy dx with a set of algebraic functions. Now these are ordinary differential equations, so we only assume variability in one axis. So dy dx is basically change in y compared to a change in x, but there can be this is true when y is a function of only x. There are no other independent variables associated with the particular equation. Now, if you have multiple uh, independent variables, then you need to differentiate with respect to each of those independent variables, not only x. So if you do only dy dx, that is differentiating with respect to x. But if you have multiple independent variables, you need to differentiate using all those independent variables. So those are known as partial differential equations. PDEs will not go into those. But if you do real world simulation and real world modeling of this kind of complex biological systems, mostly PDEs are used because there's not one single independent variable. There are a lot of independent variables that you need to manage. But coming back to here, so ODE, we'll use ODEs to model these kind of systems, and biological systems mostly will be concerned with consumption or production of a particular substrate or a particular compound or protein, etc., etc. So if you consider X as a concentration of a substrate, which can be anything, as I said, mRNA, protein, small molecule, whatever. What you want to see is like at t plus delta t time, what is the value of X? So this is the Taylor series where you can expand t plus delta t, X of t plus delta t in terms of X of t. And if you take a limit of delta t tends to 0, this forms the differential equation, which is dx dt equal to kx. So a few things about this particular equation and all um, uh, differential equations in general. So there is an order uh, um, and linearity associated with a differential equation. So first order is basically if you're the highest differential is only whatever the highest differential is. So here the highest differential is dx dt, which is one time differential. So this is the first order differential equation. If you have a d2x dt2 or a d3x dt3, something like this, those will be higher order differential equation, second order and third order. Linear because it's linearly dependent. There is no so this equation might have been like dx dt whole square equal to kx or something like this. So the highest uh, power or the highest power of your differential is 1. So that's a linear. There's a linear relationship between your differential and your expression of your right hand side. So that's a linear differential equation, and this is autonomous as well because it does not depend on any other kind of independent variable. So this is linear first order autonomous ordinary differential equation. So here x is your independent variable, which is your state variable. Here x you considered as the concentration of the substrate. K is the parameter because it's a so when you say dx dt equal to kx, what it means is that your dx dt is proportional to x. You add a proportionally constant k on top of that, which is actually your parameter, and this k will differ from different will differ under different conditions, different equations, different substrates, different molecules that you are using. This is in general, if you recall class 12 chemical kinetics, this is the first order uh, chemical kinetic equation, right? So yeah, and in this case, your parameter K denotes the reaction rate of how fast or how slow the reaction is going. Okay, so I think that's a good introduction about what are ODs and how we use ODs and like what are the different caveats of ODs. Now you have this equation dx dt equal to kx. You are asked to solve this equation. So this is a very simple equation. You can just separate out the variables on both sides. So on the left hand side you have a slash is missing here, by the way. So this is dx by x equal to k dt. So your x is on one side, your independent variable sorry, your dependent variable is on one side and your independent variable t is on the other side. Then you can integrate directly with a certain limit. This limit goes from x naught to xt, and this goes from 0 to t, right? And if you integrate dx by dx, integration brings up log x, and this is a simple kt. And if you simplify this equation, this becomes log of xt equal to log of x naught plus kt. And this x naught is the initial condition of the system. So when you're integrating from x naught to x naught is the initial condition of the system, basically telling you you started from this amount of substrate or this amount of protein or whatever molecule you're trying to study. So it's a constant, and uh, it's basically giving you the boundary conditions, the initial condition of this particular reaction. And if you do an exponentiating of this thing, basically bring so this ln log of xt by x naught, if you take an anti-log, xt by x naught becomes e to the power kt. And if you put x naught on the right hand side, this equation comes out, xt equal to x naught e to the power kt. So like if you have a simple first order differential equation where you can just separate out the variables on the left and the right hand side, you can directly do an integration and find out what is the equation. But in most cases, in most real life cases, and in most differential equations, you'll find that this does not hold because this is a very simple equation. In most cases, we'll have a very complicated three, four variables included, PDs together, everything, and you cannot just do a simple integration. So there are methods to uh, solve a differential equation where you cannot directly solve it using analytical methods. We have numerical methods for that. Okay, a little bit on how this equation works and what it actually means. So this was your original problem statement. You started with a constant with a substrate, and you want to see want to trace the path of how it's formed into a product using a particular equation. So, and you got this particular equation integrating the original differential equation. Now, what does this equation actually mean, and what does this signify? So, as I was saying, the parameter k is of utter importance because depending on k, uh, sorry, someone saying anything? Okay. Okay. Yeah, this parameter k is of utmost importance because this k is specific to specific equations, specific molecules, specific conditions of the equations as well, the temperature, the pressure, of the, whatever conditions that is there in the there for this particular reaction to happen. So depending on the value of k, your system will behave differently. So this is a good example for this. If you take k is greater than 0, so this becomes, say, let's take k equal to up like 2 or 3 or whatever. So this becomes xt equal to x naught e to the power 2t, the curve of which looks something like this. So it's an exponential growth curve. So it's growing at an exponential rate. Now, if you take k as negative, this becomes a negative k. It becomes a negative exponential, which is e to the power minus 1, minus t or minus 2t or whatever. It becomes an exponential decay. So depending, it's the same equation, but depending on the parameter value of k, uh, it can either be a exponential growth equation, it can be an equation describing exponential growth, or it can be an equation describing exponential decay. So the value of k, again, I'm reiterating, the value of k is actually very important. Parameter, the value of the parameters of your differential equation is very important to explain the system that you're working with. Okay, so now this you have discerned what is the behavior of the equation, behavior of your system across a certain time. So here basically 0 to t, both of them 0 to t. Depending on k, this is how your system will behave. This is how x will change with t, right? Now, if you are asked what is the steady state behavior of this particular system, now recall in the first few classes we talked about steady states. So again, reiterating the fact. So there are, the steady state is the state of the system where it's basically it's at a net zero uh, uh, profit or loss, you can say. So basically something like that. So basically when your system is at steady state, it does not it is not being able to change the state of its own system by its own. So it needs an external stimuli to change the state of the system. Steady state is basically when your change of the system is zero. So mathematically, that is defined as the x equal to zero. So where your x and your t, your x is basically not changing with time. So your the concentration of your substrate or the concentration of the reactants that you're working with, that does not change over time, that is constant, and basically a reaction starts off with whatever the reaction is. So if it's a catalysis reaction, it'll start off as a catalysis reaction. There will be some shift in the system, but at a certain point of time, after a certain point of time, the system will reach steady state, and x will not change with time. So if you consider these two, both of these graphs, so what can happen is, in exponential growth there is no steady state because it will grow and grow and grow and grow. But in exponential decay, what will happen is it comes down until after a certain point of time, this will become a flat line. This becomes a line that is almost a tangent to the x-axis, parallel to the x-axis. So that is the point of time at which steady state is achieved in this particular reaction. Now, So yeah, mathematically that is how we define where is dx dt equal to 0. You can think it from a mathematical perspective as well. So when your dx dt equal to 0, the slope of your curve is 0. Right. So it's basically a curve that is parallel to your x-axis. So it's basically a stagnating curve. So yeah, so if your dx dt equal to 0, the rate does not change and the ODE stays there forever. So basically the system, in this case, ODE is not a good word to use. The system stays there forever. Now, there can be two types of steady state as we had discussed earlier. So you can have an unstable steady state and a stable steady state. The unstable steady state is basically if you give an external stimuli and try to move the system out of that particular steady state, what it'll do is it'll permanently move out of that steady state if it's an unstable steady state. If it's a stable steady state, what you'll do is if you put an external stimuli to move it out of the out of that particular state, it'll after some time it'll come back to that state because it's stable and it's a steady state, right? So these are the two types of stable and unstable steady states as we have. Now, how do you determine mathematically if a particular steady state is stable or unstable? So it's actually quite simple. So for example, in this equation only, let's take that example of this equation only. So xt equal to x naught e to the power kt, and you have two conditions k equal to 0 and k greater than 0 and k less than 0. Now, so at dx dt equal to 0, uh, w- uh, if it's sorry, if you uh, so at dx dt equal to 0 is your steady state. So if your dx dt equal to 0, your kx equal to 0 because this was the equation. If you recall, if your dx dt equal to 0 here, your x is 0 as well, right? Because your k is non-zero, the x is 0. So uh, th this is your steady state condition. Now, uh, if you do what is the value of dx dt at when epsilon is negative. Epsilon is basically the initial initial state of the reaction. So x naught is basically the initial condition of the reaction. So if your initial condition is less than 0, that means your dxdt is negative, right? And if your initial condition is greater than 0, that means your dxdt is positive. So what happens is, like, I think, don't think this is a very good slide to explain stability, steady state stability. So assume, I'm not sure if I can draw here. I'll try. So basically, you have a curve. So let's assume this curve goes up, goes up, goes up, and it attains a steady state like this. So let me write it here. Yeah. So yeah, this is your y, x, and it goes up, and attains a steady state here. Now, what you need to do is, if you need to find if that particular state here is actually a stable steady state or unstable steady state. I hope you can see the page anyway. So to do that, you need to find if this point is actually a minima or a maxima. If this point is actually a maxima, then this state is unstable, right? So how do you define a maxima or a minima? You differentiate the equation. So in that case, you need to find d2x dt2, right? If your d2x dt2 is less than 0, if it's a minima, then it's unstable, then it's stable. If it's a maxima, d2x dt2 is uh, greater than 0, then it's a unstable steady state. So I'll just draw and show you. So if I complete the curve like this, so a curve goes going like this and it falls off like this. Now assume a steady state here. Here your dx/dt is 0 because it's parallel to the x-axis. Now as- think in terms of what a stable steady state means or an unstable steady state means. So unstable steady state is if I just push this, will it come back to its original position or will it move away? Most probably it will move away because the energy is lower in this point of space. Now, if it would have been a stable steady state, so this is the maxima. So in the maxima, if you have the steady state, if you push it, it will move away. So it's likely an unstable steady state. But if you have a curve, say like this, the lower one. At this point also, this is a steady state because this is parallel to x-axis. The slope is 0 here. But if you push this away from here to here, this will generally come back to the original steady state. So this is a stable steady state. So if it's a maxima, the chances are that it's an unstable steady state. If it's a minima of the whole equation, there are chances that it can be a stable steady state. Okay, so I'm skipping this slide because this is a little bit different to how I explained, but this actually also holds. So yeah, okay. Now, how do we model different equations? Like, so here are a few examples of this. So for example, this is a biomolecular reaction where you have two components X and Y with a reaction rate K. It's producing a compound Z. In the other case, you have a dissociation where Z is being broken down into X and Y. And the third case is a reversible reaction where X and Y is forming Z, and also the reverse is true. Z is also forming X and Y. Now, the first equation, it's you can write a differential equation on the particular substrates based on each of the particular substrates. So let's take the example of the first one, X. How is X changing with time? dx dt is the rate of change of X with time. Now, here, if there would have been a coefficient, that coefficient would also have been carried forward in this equation here, but here there is no coefficient. But there is a reaction rate K, but it's on the negative end. Like X is getting broken down, X is not getting formed, so it's negative. K K is negative. It depends on X and depends on Y. The concentration of both is required to actually convert X to Z, right? So it's dependent on the concentration of X, concentration of Y, and so basically assume it like dxdt is proportional to X star Y, like X into Y. Now, if to remove the proportionality constant, you need remove the proportionality sign, you need a constant and a proportionality constant to be introduced. In this case, the proportionality constant is negative of K. Why negative? Because X is getting used up. X is not getting formed. So X is getting used up, so a negative K is involved in that. Similarly with Y, if you write an equation of dy dt, the rate of change of Y depends on the concentration of Y and the concentration of X, and it's a negative K because Y is also getting used up. For Z, however, the K is positive because Z is getting formed, and the rate of change of Z also depends on X and Y. So dz dt will be K into X into Y. Okay, so I think this is fairly simple to understand. So you need to keep in mind if your particular substrate, if your particular compound is getting formed or dissociated. If it's getting formed, the concentration is increasing. It parameter used will be a positive one. If your concentration is decreasing, the parameter used is a negative one. So that's quite straightforward. Now, if you go to go to dissociation, Z is getting broken down into X and Y. So dz dt will be with a negative K, and it only depends on the concentration of Z because it's a spontaneous dissociation. So K is there and K is getting, sorry, Z is there and Z is getting broken down into X and Y. So this is a spontaneous dissociation reaction. So the rate of change of Z does not depend on the concentration of X and Y. So dz dt will be minus kz, dy dt only depends on Z, but Y is getting formed. So dy dt is positive of kz, and dx dt is also positive of kz. Similarly. Now you have the reversible dissociation reaction where basically X and Y is forming Z. Again, Z is getting broken down to form X and Y again. And there are two rates of reaction involved. So the positive reaction rate is given by K plus, and the negative rate of reaction, which is basically the dissociation of Z into X plus Y, is given by K minus. Now, now if you want to write the equation for dx dt, so X, there are two components of the equation. So one, X is getting used up to form Z, and again Z is getting broken down to form X. So there are two components. So firstly is X is getting used up to form Z. So there's a negative of K plus, So this is k plus and x is getting used up. So negative of k plus into x into y. Same thing that we discussed here. That is there. And the second part is z is getting used up to form x and y, which is in this case your k negative will be positive actually. So plus of k minus into z. So you have to be a little careful about how your particular substrate or particular compound is getting used up or getting formed even. So both of the things can happen at once. And while you are writing the ODEs, you need to keep that in mind as well. So similarly with y is actually exactly similar as x because it is getting formed with k negative rate and it is getting used up with k positive rate. So right, it's the same as dx dt. Right? If you go for dy dt, so sorry, dz dt, so z is getting formed by x and y with positive k, and z is getting used up to form x and y with a negative k. So the formation of z is given by k plus and the concentration of x and y. So k plus and x and y, and there's a positive sign because z is getting formed. Now, if z is getting used up in the opposite direction, it is getting used up with the rate of k minus, and it's the only uh, um, only compound that is relevant here is z because you do not need x and y to dissociate z. Z is spontaneously getting dissociated with x and y. So the concentrations of x and y don't matter. The concentration of z matters here. So this is actually a few examples that I wanted to show about how uh, you can convert a differential equation, a reaction, a biological reaction, into a differential equation. Some of this is kind of a recap of, like, say, class 12 chemical kinetics and equilibrium and so on. But yeah, so this is how actually you can switch between reactions and differential equations. Right. Now, on top of this, if you're given equations like this, on top of this, you can have a lot of uh, laws involved to govern this particular reaction. So one will be a very simple conservation of mass. So uh, the point is the concentration of x plus z and the concentration of z plus y, sorry, y actually remains constant across all. So if you do that, you can reduce the number of systems. So these are the three equations for the last, sorry, for the last reversible dissociation. And your condition is that your x plus z and y plus z is always constant because z is getting formed from either of x and y. So x plus z and y plus z will always be constant across the timeline of the reaction. Now, if you consider this, so what it means is d dt of x plus z equal to 0, d dt of y plus z equal to 0. Now, if you expand this, this is what it becomes. Now, if you, uh, just a second. Yeah, if you replace x here, so basically this is the last equation, dz dt of equal to k plus x y minus k of minus k of negative into z. Now, if you replace x and y with a naught minus z and b naught minus z, so this is your a naught minus z and b naught minus z will come from here. So if this is your differential equation, if you integrate this, x plus z becomes x naught plus z naught, which are both of them are constant. So you can assume that sum of the constant is another constant, which is a naught. Similarly, with dy plus d of y plus z dt, if you integrate this becomes y plus z equal to a sum of constants y naught plus z naught, which becomes another constant, which is b naught. Now, if you take x and y from this equation, so x becomes a naught minus z, y becomes b naught minus z, and you put them in this particular equation. So your number of basically three differential equation come down to one equation only, and this is your particular set of two. Basically, this is your particular set of equations that you can use to describe this particular reaction. Previously, we were using three equations. Now it's a case of two equations with scalar ODU. So this becomes a lot more easier to analytically handle this kind of particular equations. So conservation of mass is one such example. There can be a lot of laws that can be used. We'll see a few examples on the way, but yeah, if you so conservation of mass is again something that is based on the system. So you know that in the biological system, the mass is conserved. In some cases, what can happen is the total amount of product can be conserved, or whatever. There can be a set of constant equations that govern this particular ODEs, and you can use those constraints to actually simplify the ODEs and solve this. So that is the whole idea. Okay. Now, as I was talking about, the ODs are good and all fine, but if a ODE becomes too complicated, and like which is 99% of a case, you will not have analytical solutions for that particular ODE. Just cannot integrate and give a equation. It won't work like that because there are no fixed. There are no the expressions become so complicated, so it's not possible to integrate like that. So the alternate option to that is using numerical solutions. So one of them is basically Newton-Raphson method. So what do we mean by numerical solutions to differential equations? So it's basically an approximate solution uh, for the whole equation, and it's almost, you can imagine, by trial and error. So not trial and error, you give a particular set of you assume a particular set of values for a particular variable, and you try to find out what are the particular values of the other variable, and you kind of get a generalized behavior of the whole system. So this is a little bit approximated. It will never give you the exact solution. This is always an approximate solution, but it tells you fairly well about how the system is behaving. Okay. Uh, yeah, so in solving a differential equation for approximate solution, you find numerical values of y1, y2, y3 corresponding to given numerical values of the independent variable, assuming y is your dependent variable, x is your independent variable. So you assume some values of x, and you find out what are the values of y. And if you plot them, you can get an idea of about how the system is working. Right? Okay, so the first one is Euler method. So it's actually quite simple. So yeah, so in solving a first order ODE by numerical methods, you can come across two types of solutions. First is series solutions of y in terms of x, which will yield the value of y at particular value of x by direct substitution in the series solution, and the values of y specified at the values of x. So Uh, this is a set of points that you are assuming, and this x is your independent variable. So x is x naught, x1, x2, etc. And you're assuming that the difference, so x1 minus x of I minus 1 is h. The difference between I and I minus 1. So this is not 1. This is actually I. This is a slight misprint here. So xi minus xi minus 1 is h. That is constant. So that's a trick to be used while you are finding the numerical solution. So so if you simplify that, it becomes xi equal to x naught plus ih. And if you put the value of I depending on 0, 1, 2, whatever you put it, then you can solve the value for x as well. So if you solve this whole thing, so y minus y naught. So what this equation is, if you try to imagine this equation, so y minus y naught is basically difference in y of equal to y prime of x naught y naught. So what is y prime of x naught y naught? So the slope of the equation at the point of x naught y naught, that is y prime at x naught y naught, into x minus x naught. So this is actually the differential formula. So how do you define dy dx? So I'll just write it here, and I think that will be better. So you write dy dx equal to y naught minus y1 by x naught minus x1, assuming that the differences are very low. So this is how you write a differential equation. This is what it means. So it's the same thing written there actually. Uh, it's the same thing written in the screen actually. So this dy dx is subbed off as y prime. And if you consider this as y prime, and then you just cross multiply, then you get that equation y minus y naught equal to y prime into x minus x naught. That is the whole idea, and it's quite fairly simple to use. Right. I have not included particular examples for these, but I actually have a lot of examples to be uh, to be worked on if you want. So either what we can do is uh, maybe in the next few classes, in somewhere I can like help you solve certain problems hands-on using different numerical methods, Euler methods, there's Newton-Raphson. Sorry, there's the Runge-Kutta order method as well. Generally, these three methods are studied for numerical methods, so I can iterate over them and maybe solve a few problems which can help you understand that. But right now I don't have the time in this class, so either I can do it sometime later, maybe in the future classes, or in the end of this particular 12 weeks, after the 12 week, we'll have another week of 2 hours where I can go over the whole course. And maybe in that one, I'll solve a few problems of these kind. Okay. I've not put an example here. So yeah. Okay. Now we come to a very important part of this of solving the ODEs and getting to know the system is the estimation of the parameter, the K. How does the K look? Now, how it is estimated, there are various techniques. There's a branch of science that deals with parameter estimation. So that's estimation theory. If somebody has ever taken up statistics, they'll know there's a separate branch of science dealing with estimation of parameters, and there are number of ways you can do it, and a lot of complicated ways as well. But simply speaking, what do you mean by parameter estimation? So depending, I'll read from here only. Mathematical modeling is an essential tool for systems biology, and to ensure the accuracy of the mathematical models, the model parameters, in our case that K value, must be estimated using experimental data, a process which is called as regression. I hope a lot of people have heard of regression. So what you do is have a simulated set of data points from your so you I'll go back to that equation. Yeah, so you have that equation. You can have like a simulated set of values for this particular equation for different values of k. So here we assumed k greater than 0 and less than 0. So you can assume different values of k, and you can have a set of solutions of this particular equation. Now what you do is you try to regress the results of your model with the results of actual experimental data, and then you see what is the best value of k that explains the real world data in terms of your equation. Right? It's the whole process is complicated of finding the parameter and how to find the parameter, but the idea is simple, that you have assumed an unknown parameter in your equation, and for different and you don't know what the parameter is, the value of the parameter is, so you take various ranges of that parameter values and solve the equations for all those values. Now you take real world data from the same set of reactions or whatever you are modeling, and you try to regress this across your data and the original data. And then you find what is the value of k that best describes, and that you can use to get real world like data from your simulated equation. Right? That is the whole idea behind the estimation of the parameter. The techniques are there. So one of them is this is known as MLE, or maximum likelihood estimation. There's another called least squares fitting. These are like most common regression techniques, and they yield parameter values, and also their variance covariance matrices. And there is a lot of assumptions that goes on to find these particular parameters. Some assumptions may be that your parameters are coming from a normal distribution, or whatever. There is a lot of yeah assumptions that you can make to make your life a little bit easier and estimate the parameter. Right. Okay. So prior to regression, the structural identifiability of the models must be assessed to determine whether model parameters can uniquely be determined and what data is required to achieve that, because that is important. And after you regress and find the best case, you need to test a model's goodness of fit, determining which model among the competing ones actually best fit your data, evaluating parameter determinability, and evaluating the parameter significance. So as I was saying, which parameter actually gives you the best representation of the real world data based on your equation. That is the whole concept of parameter estimation. And that thing, this idea of like post-regression diagnosis, is known as models goodness of fit, right? This is a technical term, but the idea is same. Okay, so I'll discuss a few methods. I'll not go into very detail, but like just overview, I'll discuss a few methods of parameter estimation. The first one is linear least square method. So as the name suggests, that you have a line. So this is your basically your regression line, and these are your data points. Right. And what you want to do is you want to reduce the distance between these data points and the line, which is the which parameter k, what is the value of k for which the distance between these data points and the regression line is the least. That is the idea of linear least square method. Sorry. So it is the process of finding the best fitting curve or the best fit, best or the line of best fit for a set of data points by reducing the sum of squares from the offset of the curves of the points from the curve. During this process of finding the relation between two variables, the trend outcomes are estimated quantitatively. This is called regression analysis, as I was talking about. So the linear least square explains that the curve that best fits is represented by the property of the sum of the squares of all deviations from the given value. So basically, you are what you're summing is the distance of this particular point, square of this distance of this particular point across all points. So this is your equation. So your d square is basically your distance from that particular point uh, to the line, which is given by this yi minus fxi. So fx I is your basically the equation, and you can estimate analytically. So assume that this point is at x1 y1, and this line is passing through x0 y0. So you want to find the distance between this point and the line. So it's going to be x0 minus x1 whole square plus y0 minus y1 whole square, and take a square root of that. That will give you the distance, but you want to do square of the distance, and you add them up. So the sum of the square of the distance is giving you the total kind of an estimation about how far away your points are from the actual regression square curve. Now what you want to do is s, reduce s as much as possible. One easy way mathematically to do that is using the concept of minima and maxima that I was talking about. So you basically differentiate s with respect to your parameter and make it zero. And equate it to zero and see what is the value of your parameter k at which ds dk equal to zero. So that k is your best fit. Now you have to again estimate if that parameter is a maxima or the minima, and those kind of caveats are there, but that is the general idea. Okay, so this is
How would you choose between the perpendicular and the other offset?
sorry, I did not understand, please.
There are two kinds of offsets that you have shown in the PPT, right? Like, how would you choose between them? Is there any particular data set that you choose for one of those kind of offsets? Or?
No, so the idea is to kind of depend on what you are trying to find. So if you I'll give you an example. So for example, if you're only looking for perpendicular offsets, the idea is that your data points are already like kind of, so this is your line and they're just split up parallel to that line. So if you're considering perpendicular offsets, it's the idea is that your your variability is across both x and y, right? So if it's sorry yeah, telling correctly. So this is your regression line, this is your data point, and if you're assuming that these are perpendicular offsets, you're assuming that your variation is variation is because of both x and y variation. But if you assume vertical offsets, in this case, this one, you're assuming only variation in y. So in most cases, we'll use vertical offsets only because we have no control over x as such. The y is the predicted variable or the dependent variable that we are predicting. So the variation is in y. If we want to minimize that, that is a good strategy to have for estimating of the parameter. But again, if your data is like that, that your x and y has a certain amount of variance associated with it, then you need to look for perpendicular offsets, because in this case you're assuming that your variability is both across x and y, and in this case, you're only assuming that your variability is only across y. So depending on the problem and the thing that you're trying to answer, uh, you can use whatever. These are all techniques, right? You will use the technique that is best suited for your question. That is there at the end of the day. But how you're assuming, as I was saying, like there is a lot of assumptions while you're doing this estimation of parameters, that maybe your parameter is coming from a normal distribution, maybe it's coming from a chi-square distribution. And why are we assuming this? Because there are evidences from experimental data to show that it might come from a normal distribution, or it might come from a chi-square distribution, something like that. So those kind of evidence, those kind of assumptions become very important when you're uh, finding the parameters. So depending on your assumption, you can use whatever you like, but the difference is very minimal. It's just you're assuming that there is an x variability here as well, and in the vertical offset, you're only assuming there's a y variability. So depending on your question, you can you can use whatever that it's likely for you. Does that answer your question?
Yes, yes, thank you.
Yeah. Okay. Okay, so the next type of next method used, and this is also a very commonly used method, which is the maximum likelihood estimation. So you have, again, these are a little bit mathematical. I'll not go into the very details of the mathematics, but the idea is, so what, as the name suggests, that firstly you have to estimate the likelihood of that parameter. So you have a set of random variables or random samples, and sampling from a distribution with a parameter theta. This theta you are trying to actually estimate. In this case, our theta is k. And suppose you have observed that these are the values of these random samples that you have taken out from the distribution. If these are discrete, the likelihood function is defined like this. So the likelihood of x, y, x1, x2, xt up till xn, given this semicolon is tells you given. So given the parameter theta is the probability of x1, x2, x3, xn, and so probability given x1, x2, x3, capital Xn of these samples having these particular values given by theta. Now, how do you define this particular distribution, this particular sampling distribution that you are sampling from, x1, x2, x3, xn, this sampling distribution? That will determine how your equation looks like. Now, if you assume that this is a normal distribution, this whole thing is a normal distribution, you have sampled from a normal distribution, then you just need to replace this with the equation of a normal distribution, which looks something like this. So let me search. Yeah, it looks something like this. If you're assuming that this is coming from a chi-square distribution, it'll have a separate equation. So whatever assumption that you're making, what distribution I'm sampling from, that becomes very important when you're estimating the parameter, because that equation is what you're actually optimizing. So what you do is basically you kind of replace this particular thing with the kind of distribution that you have assumed to be to be sampled from. And what you do is basically you this equation now holds. So L of you have this particular equation on the left given theta, and on the right you have the equation of the distribution you are sampling from. Now what you do is you try to minimize this particular right hand side. You want to make d theta sorry dx d theta d theta dx as 0. You want to do what is the value of theta for which I have the maximum sorry, what is the value of x for which I have the maximum value of theta. So that is the idea behind that. So as the name suggests, that maximum likelihood estimation is basically determined. Hello.
Yeah, is it something like minimizing the chi-square value, or actually maximizing the chi-square value?
Sorry, one second. I did not hear you. Sorry.
Is it like maximizing the chi-square value from the chi-square test?
Ha,
Does
kind
that
of,
estimate?
Depending on the distribution, it will vary. But the idea is to kind of see for which value of x your theta is. So I'm getting confused here. Which value of theta your
Yeah.
x is minimum. So what is the value of theta that perfectly describes your distribution or your particular equation? That is the idea.
Right.
Now you need to maximize that variable
Likelihood
to
of,
see what is the value of their parameter. Right. I think these kind of things are better understood using examples. So I probably will like go through a few examples of these in the future classes if you
yeah.
guys
Okay.
want in the future. Yeah. Because yeah, it's easier to understand using real life examples. So, okay. Okay. So we talked about two very well-known techniques for parameter estimation. Now, the other technique, there are a lot of other techniques, but the problem uh, kind of remains similar. So, if you have say a non-linear dynamic system, which is there yeah, across all of systems biology, all the systems that we see are basically non-linear, and biology is a very dynamic system. So mostly equations you'll see are nonlinear dynamic systems, and they can be usually modeled as a nonlinear programming problem with a differential algebraic constant in the mathematical models. Now, to model the nonlinear dynamics, usually a equation like this is assumed, where so you have these parameters, these kind of variables, x, y, t, v, and t. So t is your independent variable, first of all, because you're differentiating with t. X and y it's written here only. I'll read it from you. So P is a vector of control parameters of the differential equations, which need to be estimated with an initial condition. X is your differential state variables. V is a vector of other parameters, that is parameters obtained through experimental studies on like real life data or whatever you have solid evidences of that parameter being valid. And then you have a set of other variables as well, which are basically equality and inequality constraint that express additional requirements for the system performance. So it's not only about maximizing or minimizing the parameter and getting the best fit of the system. You have to remember that the system has constraints of its own as well. So when you are writing the equations, you need to keep in mind the constraints as well. Now the constraints will also have some parameters uh, involved with those with themselves as well. So you have to assume that there is a set of parameters that are acting on the constraint, and you have to assume that those parameters are being sampled from a particular type of distribution. So this is actually the parameter estimation problem in one line, if you may say. So where you have a set of variables, which one will be a state variable, one will be a control variable, one will be a vector of your known parameters, one will be your vector of your constraints, and etc. etc. So this is how a parameter estimation problem is defined in with respect to differential equations in this case. So yeah, and see, P is also so P was a vector of control parameters which are which you want to estimate, but also that also has constraints. So there will be a lower bound, there will be an upper bound. So all of this information you need to capture and then estimate your parameter so that you can come up with a parameter that actually explains the system. So it becomes a little bit messier when you actually want to do this in real life. But yeah, the idea is to match what you see in experimental data to what you are finding in your simulations. And the parameter estimation becomes a very big problem and a very big part of that. Okay. Okay, now we come to a specific type of mathematical model and kind of one of the oldest and mathematical models that still stand the test of time. Michaelis-Menten is one of the widely studied models. So, but this is essentially a mathematical model. But when we study it in our lower classes, generally it's not expressed like that. Okay, so what does Michaelis-Menten equation tell you? So you have an enzymatic reaction which has a enzyme which converts a substrate to a product. How does it do it? This is a systematic equation that describes it. You have an enzyme and a substrate. And this part is reversible, which forms a enzyme substrate complex with a forward reaction rate of Kf and a backward reaction rate of Kr. And then this enzyme substrate complex is broken down in a non-reversible reaction to form the to replenish the enzyme and to form the product, right? If you apply laws of mass action, it states that any of the chemical reaction is directly proportional to the mass of the concentrations, product of the masses and the concentrations of reacting substrates, like we discussed in the other earlier examples as well. You can develop a system of four differential equations. So there are four major compounds involved here. One is enzyme, one is substrate, one is enzyme substrate complex, and the other is the product. So you can write differential equations for all these particular compounds. So let's quickly go through one. So dE dt is basically, so first E is getting used up to form ES. Again, E is getting formed from ES as well on the left, and also E is getting replenished from ES on the right as well. So negative of K forward of E into S, because E plus S is getting converted to ES, uh, plus positive KR because E is getting replenished here. So, and it only depends on ES, so KR of ES. And then again, ES is getting formed, sorry, E is getting formed from ES with this is the reaction rate, which is Kcat. So Kcat into ES. So like this, you can write equations for all the four compounds that are involved in this particular reaction. Right. So if in their original analysis, Michaelis and Menten assume that the substrate is in an instantaneous chemical equilibrium. Again, equilibrium is the steady state where there is no change of substrate or enzyme or product concentration, right? Uh, so yeah, that was the initial assumption of Michaelis-Menten, but then an alternative analysis was proposed 10 years later by these two people, which is known as the quasi-steady state of the system, where they assume that the concentration of the intermediate complex is approximately steady during the progression of the reaction. So what they said is this whole reaction is not in a steady state, only the concentration of ES is in a steady state, which actually it makes a lot of sense. So both these approximations assume irreversible dissociation of the ES complex to the product and free enzyme that yields the following equation of the velocity of the reaction. Now, if you actually, this is dPdt here, right here. So Kcat into ES. Now, if you replace all these equations and simplify them, this is what it comes down to. So Vmax is your maximum velocity of the reaction. Km is the Michaelis-Menten constant, and S is your substrate concentration. And this Vmax is actually given by E naught Kcat. E naught is basically the initial initial enzyme concentration, which is the same across the whole equation, and the K catalysis, which is the last part of this equation. So ES is getting broken down to E and P. So this is the equation for Michaelis-Menten that we see daily and widely used. So the velocity of the reaction, what sometimes people misunderstand what the velocity of the reaction actually means, is that it's nothing. It's just the rate of formation of product. That is the velocity of the reaction. So the curve, I hope you remember. So it's an exponential curve, and there's a stagnation that comes up about, and on the that's which is the maximum velocity, which when it reaches Vmax, and the corresponding substrate concentration correspond to Vmax by 2 is given by Km. So Yeah. So this actually this actually basically holds. So yeah, this is the Michaelis-Menten equation. Again, how we derive the Michaelis-Menten equation is through using differential equations and modeling this particular type of reaction. So that is how Michaelis-Menten is equation is actually derived. Right. Again, this model provides crucial information about the nature of the enzyme in the form of the kinetic parameters. The Michaelis constant, as I was saying, is the concentration of the substrate at which the reaction rate is half the maximum rate. So basically, Vmax by 2, the corresponding substrate concentration is given by this constant, which is Km. And yeah, and this is an inverse measure of the substrate's affinity for the enzyme. The smaller value of Km, the higher the affinity, and hence the rate will approach maximum velocity with lower S than other reactions with a lower Km. So if you have a lower Km value, uh, uh, sorry, if you have a lower Km value, you have a higher affinity for the reaction, and the rate will approach maximum velocity with a lower concentration of the substrate. Right. And yeah, and the catalytic rate kcat, which is the last part of the equation, it shows how fast the reaction is. This is also a thing, which is a kcat by km. This is also constant, and it provides knowledge on how efficiently an enzyme converts a substrate into a product. And the curve is not here, but the curve, I hope you remember, or you can just do a Google search. It's just a exponential curve with a stagnation after a certain point of time. And yeah, and if you uh, and basically that curve, how it is coming is basically describing the relationship between the velocity and the substrate concentration in the Michaelis-Menten kinetics, and they can be formulated as a non-linear regression model because of the nature of the curve. Again, the commonly used model is expressed using exponential function. This actually you can get if you do a certain manipulations of this particular equation, and this becomes Vmax into 1 minus exponential of minus b into s. So these b is another constant that is assumed. I think b here is somewhat related to kcat by km. I do not exactly remember, but anyway. And yeah, and if sorry, b is a real value parameter, and you can actually, if you know Taylor series, you can expand this up. And if you have a polynomial, and you can expand this up to the polynomial of the k degree, like this. So it's okay. We'll not go into so much details of the equation, but yeah, that is how the equation is derived. Now, there are special caveats to this equation. You can add or include certain things to this equation because this is a very straightforward equation, right? So you have an enzyme, you have a substrate, forms an enzyme substrate complex, and then it breaks down to form an enzyme and substrate, right? Now you can add certain things to it. So there can be an inhibitor, right? So where does this come along? So if you're administering a drug to a particular type of a disease, and the substrate is uh, uh, that you are targeting that also has a very similar kind of a looking substrate inside the cell. How do you know that that particular substrate will not inhibit binding of the actual substrate and the enzyme, right? So there are in real world biological systems, there will be a lot of caveats involved with this particular reaction. So one of them is basically competitive inhibition. I actually have a few kind of caveats on this, but I'll quickly go through this because I have other things to cover as well. So uh, yeah, a second substrate, which is the inhibitor, it can bind to the enzyme, and if it does, there will be no product created. So as the model will look something like this. So you have enzyme substrate, you have this reversible reaction forming the enzyme substrate complex, which gives the product and the substrate. This will be your original kinetic equation. On top of that, the inhibitor will also bind with the substrate and give an inhibitor substrate complex, but it will not give any product because it's not the actual substrate of that particular enzyme, but it will form this particular reaction where it will use up your enzyme and it will form that enzyme inhibitor complex. So competitive inhibition can be explained by using these two particular equations. Now, how do you model that? Let's quickly say that the modeling, as you can see, there's a lot of equations involved. So first, you model dSdt. So dSdt only depends on this particular reaction, which is positive K1, sorry, negative K1 and negative positive of K minus 1, right? So yeah, negative K1 and positive K minus 1. If you want to, sorry, if you want to do for E, you do a similar thing like this you do for all. So C1, C2. C1 is actually the enzyme substrate complex. Now C2 is the enzyme inhibitor complex, right? So you write differential equations for all these. Now you reduce the number of differential equations as we discussed using conservation laws. So in this case, C1, C2 plus E is actually a constant. So C1, C2 and the enzyme. It's actually constant. First of all, the enzyme remains constant across the whole reaction, and the enzyme substrate complex will also remain constant across both the reactions because the enzyme is remaining constant as well. So whole together, all of them actually is added up is a constant. And the other constant equation is I plus C2. So the inhibitor is, you are assuming it's in an equilibrium state. So inhibitor and your C2 is also in an equilibrium and it's constant. So these two assumptions you make, and then you substitute the values of, I think in this first case, you substitute the values of E to this particular value. So E is basically E naught minus C1 minus C2. You substitute this like this. You substitute with the rest of the equations, and you are actually left with three equations: dsdt, dc1 dt, and dc2 dt. And the quasi-state approximation, as these two people said, is basically that your enzyme substrate complex is in equilibrium, not the whole thing. So in this case, your C1 and C2 are in equilibrium, not the whole thing. So if those are in equilibrium, so dC1 D2 dt and dC2 dt both equal to 0. Now if you like put this here and solve the equation, you get all these values where basically this theta is, I think, another constant which comes in as a parameter of the equations as well. So yeah, so in this case, your dp dt, if you substitute all these values, c1, k2, whatever this there, okay, the theta I is defined as the k minus 3 and k3. So this thing, this the ratio of this is given by theta I. Anyway, so you can just replace these particular equations and kind of make your particular model a little bit simpler, and then estimate the values. So this is what the product formation rate gives you. This is the equation of the product formation rate in presence of a competitive inhibition. Now, how do you estimate the parameters? The parameter here is theta, right? How do you estimate the parameter theta here? What do? You take a real life example of the same competitive inhibition going on in a cell. You have the data of how much and what is the rate of the product formation, and you regress that original data with the simulated data of this particular equation, and then try to do the estimation theory techniques, reduce least square, or do a multiple likelihood maximum likelihood estimation, or whatever. So you uh, that is actually the way about how it works. So you have a system, you have a you make a set of equations, differential equations. You try to solve them, make them simpler. If it's not solvable, then you have a equation like this, where you can have simulated values for different rates of product formation, and you have also real world data of different rates of product formation, and then you can do a regression and estimate the parameter which best fits in your case, right? So this was an example for competitive inhibition. Similar is an example for cooperativity. It's basically when n molecules of a substrate must fit together with the enzyme in order for the reaction to take place. So it will not only work with one substrate, one particular molecule of a substrate. It will work with like 5, 6 molecules of substrate. So yeah, so uh, actually, I'll not go into the details of these equations. So actually, this is the equation, and if you do a OD model, this will turn out this will be the differential equations that turn out. But after you do a steady state approximation, quasi steady state approximation, what you find is this function is basically dp equal to Vm s to the power n by theta plus s to the power n. This is actually the form of a Hill function that we always define while defining interaction between two molecules inside the cell. That can be a gene and a transcription factor, that can be a protein, that can be something. Like if you can assume this to be a gene, so this assume this is a promoter of a gene. Now, three transcription factors has to come and bind, and after that only the gene expression will start. So the situation is very similar, right? So you can use this kind of conditions and equations to describe your particular system. And this actually forms the Hill function. And if you just modify the theta to the power n, this is actually the form of the Hill function, Vm s to the power n by theta to the power n plus s to the power n. The value of n actually determines if it's a dissociation or an association or whatever. We'll come to it a little bit later. But yeah, this is actually the formation of a Hill function. Okay, so what the Hill function?
Is
Yeah,
theta similar to like Michaelis Menten constant, or does it diverge from there? Is it something different?
uh, which one is similar? Are you asking?
Theta.
Kind of. Yeah, the form is similar, but again, the usage is different. So Michaelis-Menten, if you use it directly, it's kind of a one-to-one reaction that is taking place there. So here the caveat is a little bit more. It's not a one-to-one. You have certain molecules of a substrate to come and bind to the enzyme, and then the enzyme to start using that. So it will be kind of a sigmoidal response that I'll talk about in the next slides. So it like the initial set of initial set of binding will form start the reaction in a slow bit, but when all the substrates actually bind to the enzyme, it'll go off. So this actually gives you the sigmoidal response curve. So if you notice, this is very similar to the Michaelis-Menten curve. Uh, if it's a sigmoidal, sorry, if it's a hyperbolic, it's actually Michaelis-Menten. If it's actually sigmoidal, it's more of a Hill function, right? So slight differences, but yeah, the form is similar. It's not that drastically different. Okay, yeah. So yeah, that is what actually I was saying. So from Hill equation, these are the type of curves that you get. You have a sigmoidal kind of a curve compared to a hyperbolic curve that you have from a Michaelis-Menten equation. So for positive growth, uh, this is what it looks like. Initial set of initial time, the substrate grows very slowly. Then there is a jump when the full formation is reached, and then it plateaus out. And similar is the case for negative growth, which basically uh, uh, the 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 concentration reduces and then it reaches a plateau. And yeah, and this is different from uh, Michaelis-Menten and the sigma hyperbolic curve by the fact that if your theta to the power n, the value of n is equal to 1, this becomes a hyperbolic curve, which is similar to your Michaelis-Menten. But if your n is greater than 1, it becomes a sigmoidal curve. And if its n is less than 1, it becomes a like this curve, basically, the opposite of the sigmoidal curve. So convex or concave, depending on that. On different values of n, so if you're varying the value of n, the if you increase the value of n, the more sigmoidal it becomes, the more it shifts away from a hyperbolic curve. So yeah, it and if it becomes a fully sigmoidal curve like this, yeah,
Doesn't n represent the number of molecules that are required on the enzyme?
yeah, we will come to that. No, no. So we okay, let's go there only. Okay, so this is your Hill function equation. Your that theta is being replaced. Uh, Sorry, what was the equation there? Yeah, yeah. So basically, what Hill function tells you. So this is actually the form of the Hill function. So your theta is the fraction of the receptor protein concentration that is bound to the ligand, which is basically the concentration of your enzyme substrate complex, right? The fraction it is given as a fraction, but it's actually telling you the enzyme substrate, how much of the enzyme substrate complex has been formed. So the fraction of the receptor protein concentration that is bound to the ligand, this is on top is a free ligand. This is your constant for dissociation or association or whatever, which is given by theta. And n you are talking about, this is actually not, this is actually the Hill's coefficient. And depending on the value of n, so if n is greater than 1, it becomes a positive binding. If it's less than 1, it becomes a negative binding. And if n equal to 1, it becomes the hyperbolic curve from the Michaelis-Menten equation. So in this, what you are suggesting is basically the number of molecules. It's not exactly a one-to-one mapping with the number of molecules. It's basically telling you about what is the cooperativity between your enzyme and your substrate. That is what n tells you. It's not
In case n is less than 1,
huh.
does it mean that more than one receptor is required for the, whatever processing to be happening?
uh,
Like a single molecule of the substrate is being processed by one or more than one receptors or enzymes.
no, I don't think like it's. I think you're getting a little confused. That has got nothing to do with n. N is basically telling you what type of reaction it is. Is it a basically a
No, I
cooperative
understand. It's like,
process? Yeah,
yeah, but like when you're thinking about the number of molecules involved, if n is greater than one, then you would require more than one molecules for uh, the reaction to complete, right? Substrate
yeah,
molecules.
yeah.
So when it goes to lesser than one, would it mean that there's more receptor that is required or something like that?
Mm, I
What is
got
the
a question. I
physical
got a
characteristic
question,
of?
but I'm not sure about that. I don't know. I have to look up.
Okay, yeah,
Okay,
sure.
so yeah, okay, I'll keep this in mind. But I do not recall any such thing. But okay, I'll look it up. So you're saying ki, like if the value of n actually determine, so if n is greater than 1, you're saying ki, like there is a good positive cooperative binding, and that is the reaction is going on. And for n less than 1, you're asking if there like the full binding has not occurred, you need more molecules for binding, and then the reaction will occur. Something like this you're asking, right?
Yeah, somewhat like that, yeah.
Okay. I'm like 70% sure that is not the case, but like I'll check, and I'll maybe let you know in the next class.
Okay, thank you.
Yeah. Okay, so yeah, we're talking about these, and yeah, so one thing that we need to talk about here is the sigmoidal curve. So the what how it is different from the hyperbolic curve is, so this actually, if you imagine this as a switch, so if your curve is very sigmoidal, so if you assume that this is your curve and this just goes from here to straight line as a straight line to here, and then it stagnates again. So how it acts like is a switch. So at so if you assume this is a values of concentration, so at this particular concentration, the the uh, the the cooperativity or the binding of the molecules is at a very low rate. But once you once you cross this particular concentration, it shoots up and it becomes very high. So it's kind of a switch. If you turn off on that switch, all the binding occurs. If you turn off that switch, all the binding actually the binding does not occur, and it's like very weak binding. So this is actually very important in terms of stability. So switching from one state to another is very important in these kind of situations, because like it will tell you about the stability of the system. So if your system does not want to switch from one state to another, what it means that the system is in a very stable state. And if it generally, like if it with slight increase of concentration, it rapidly shoots up to another state, what it means was either it was not in a steady state or it was in an unstable steady state. So that thought is also very important in our case. So uh, there comes the concept of multi-stability. So this equation will follow me will basically take a few examples from this equation as well. So yeah, so if you have an enzymatic reaction like this, and you assume that this is an autocatalytic process, so it's the enzymes and the concentration substrate concentration are on in equilibrium and is catalyzing it on its own, and P enhances its own concentration. So there is uh, So there is an accumulation of P inside the system. So it is getting enhanced slowly and slowly. So and it has a system to enhance its own concentration. And then you have a degradation rate as well, where by which this particular product will be used up by other systems and other pathways and metabolic pathways. So this is what the equation becomes. So in this one, so for S, you uh, replace it with alpha P, which is basically is like the relationship between the substrate and the product, assuming there's a alpha rate of reaction, meaning like it's not as it's kind of you can assume it's pseudo parameter that you are assuming because this reaction is directly not happening. Substrate to product, there are a lot of things involved in between. So if you just assume that, let's for simplicity assume that's a steady rate with alpha, and you assume S equal to alpha P, and you replace these particular values with alpha p, and you add a dissociation degradation constant as well, which is gamma p. Uh, and for approximation, they have taken alpha, gamma, and Vm as equal to 1. So this is what your particular equation becomes. Now, what are the possible states of this particular equation? So at steady state, dp dt equal to 0. So if you put dp dt equal to 0, p becomes p to the power n by theta to the power n plus p to the power n. So this is actually your so there will be two cases. So one, so depending on the value of n, there will be two cases. So one is the hyperbolic case where A is in unstable equilibrium point. So here I will just zoom in here. So A is an unstable equilibrium point. B is your stable equilibrium point. Is this point, and this green line is giving you the degradation rate, and this is your production rate, right? So these in these 2 points are actually stable points, but this is an unstable point. This is sorry, these are steady state points. This is an unstable steady state point. This is a stable steady state point, right? And PT converges uniquely to a intermediate value. So this actually converges to a particular stagnates to a particular intermediate value. The other thing that can happen is basically it's a sigmoidal curve, as I was talking about. So you have it's kind of acting like a switch. So you have a small increase in y, small increase in p after a certain period of time, but then suddenly it jumps to a very higher value. So that's the sigmoidal case where actually it's opposite. This point is a unstable equilibrium point, and these are B is a stable. Sorry, A is an unstable equilibrium point. On the left hand side, it is an unstable equilibrium point. This is a stable equilibrium. This again is unstable. Sorry, I think I said it wrong. So A is stable, B is unstable, and this is stable. Huh. So it's stable, unstable, and stable again, like that. So and PT converges either at A or C depending on the initial uh, condition. So what it is showing you is you have a steady state here, stable steady state. A is your stable equilibrium point. You have a stable steady state here. You have an unstable steady state in the middle, and then you have another steady state sometime later. So you have two steady states and an unstable, two stable steady state separated by a distance, and in between that you have an unstable steady state. So if you are moving from from stable steady state 1 to stable steady state 2, you have to go through that unstable steady state, but the whole system is showing two stable steady states, right? So this is what is known as bistability. So a system that can exist in two stable steady states and can switch between them. How does it switch? Depending on the sigmoidal curve. If it is too steep, it will switch like very instantaneously. If it's like a little bit more curved like this, it will take some time to switch between different states. But what it is essentially showing you is a bistability condition, or it is also known as bifurcation. So basically, you have two states in which the system is stable, and it can switch between one state to another depending on the different parameters and different conditions. Right. So this actually is a very important point in terms of understanding systems. So biological systems have multi-stable conditions. So it is stable across many different states of the system, and it can switch between these states of the system. So how it switches and why it switches and when it switches, that is a very important question to understand the biology of the system, right? So, for example, I'll give you an example. There is in cancer biology, so there is a phenomenon called epithelial to mesenchymal transition. So epithelial state are states of the cell where it has certain cell extensions where it can bind to the cell matrix, and the cell does not actually flow away. It's not in a flowing state. It's in a very hard bound steady state. Right? It binds to that particular layer and it rests there. It does not move from there. And there is another end of like this is one property of the cell, and towards the end of the spectrum of the same property, opposite end of the spectrum, uh, is basically the cell has floating capabilities, the cell has moving capabilities. So when a cancer is formed, uh, these epithelial cells, actually a very common type of cancer is this epithelial cell cancer, which is found in lungs and in other tissues as well. So after cancer is formed, so it will try to metastasize. So it will try to move from one part of the body to the other part of the body. How does it do that? It flows through the blood, and it goes and like spreads the cancer to other parts of the body as well. Sorry, you were saying something? Okay. Yeah. So what happens is initially that they were a set of epithelial cells, but when the cancer occurred, some of those cells were transformed into mesenchymal cells. So the epithelial properties of like standing your ground and being at that point was lost, and the same cells actually showed mesenchymal properties that can flow through the cell, that can move from one point of the body to another. So this transition between epithelial and mesenchymal, this actually has a lot of impact on tumorigenesis and metastasis of cancers. Now you think about it, it's the same cell that is showing the characteristics of an epithelial cell and the same cell that is showing the characteristic of mesenchymal cell. But both the cell states are like stable, steady states. They are not like in an unstable condition. When it is showing epithelial properties, it's not in an unstable conditions. Neither is it in an unstable condition when it is showing mesenchymal properties. But this transition occurs in the same cell from epithelial to mesenchymal and mesenchymal to epithelial. So these are two steady states in the cell, but the cell can switch between these depending on the conditions. So multi-stability or bistability is a very uh, well-known phenomenon in biological systems, because a same cell or a same system can exhibit different steady states, and in different steady state it will exhibit different properties of the cell. So these kind of conditions, these Hill equations, this type of modeling is very well used to understand different steady states of the cell and how it can behave when a particular phenotype occurs. So we can predict how a particular cell, after being hit with cancer, will try to metastasize. So it is a very important, big and important thing, right? So yeah, I just wanted to give you an example. So I myself have done a little bit of work in this EMT and transitions and all. But yeah, this is actually a very good example of actually looking into multi-stability and bistability. So yeah, maybe you can take up this example and read up on it a little bit. You'll find this a lot intriguing. Sorry. Okay.
Is there an intermediate adherent state for that?
Yeah, so the idea is, so you have an epithelial state and then mesenchymal state, and there is a hybrid state in between, where it shows both properties of epithelial and mesenchymal states. And that actually is the most harmful cell type of all in terms of tumorigenesis. So that is the cell type that can cause the most harm in terms of formation of tumors and uh, like kind of flowing of these tumor cells from one part of the body to another. You have to remember that once the cells metastasize and go to a different part of the body,
Like
there
adhere again.
there it has to switch from the mesenchymal to the epithelial state back so that it can form the tumor there. So the switching has to be there. So for that to be there, you cannot fully become a mesenchymal cell or fully become an epithelial cell. You
Yes, yes.
have to be some sort of in the middle to become a hybrid kind of a phenotype and hybrid kind of a cell, so that you can switch to either states whenever and wherever you want.
So is that also another stable steady state, or is it
Yeah, it
unstable state?
is. It is stable state. It is actually the state.
Okay, okay.
The state is actually, it goes from, like, it goes like this, then it forms a steady state, then it goes further up and forms a steady state.
So
So three
you
different
can
steady states.
understand it as three different stable steady states.
Yep, yep, yep.
Okay, okay.
So this kind of examples you'll find a lot in biological systems. So yeah. Okay. I'll skip feedback regulation. I'll go through this one. Gene regulatory network. Okay. Uh, yeah, I think this is fine. Okay. So you have a gene regulatory network. You have two genes, gene A, gene B, and you have two. So these genes will form two RNAs, RNA A and RNA B. Sorry, and each of them will form a particular protein, protein A and protein B. Now, these particular proteins, so protein B regulates gene A and protein A regulates gene B. So this is a very simple gene regulatory network where you have two genes and the products of those two genes actually regulate one another. So in this kind of system, uh, uh, what are what is the kind of a model you can make? You can basically try to understand what. So the relationships also are a little bit different. If you notice, protein A actually uh, accelerates the expression of gene A, while protein B accelerates the expression of gene A, and protein A uh, decelerates or inhibits the expression of gene B. So if you follow the Hill function and basically, uh, sorry, yeah, so actually this equation they have used there. So I'll anyways then say this about. So feedback regulation is this process is known as feedback regulation. So you have a product that is getting formed that again in turn regulates some other product or itself as well. So this is not exactly feedback, but it's like cross feedback. It would have been exactly feedback if protein A like kind of control the expression of gene A and protein B control the expression of gene B. So it's not exactly feedback, but it's kind of cross feedback. So yeah, so you can
Something
have,
like catabolic repression.
sorry,
Something like catabolic repression.
yeah, kind of, yeah, yeah, that's a good example. Catabolic repression is something similar. So this is actually I think Lac-Operon also kind of operates in a similar kind of way. So you have a set of products that actually like set of genes and a set of products, and these products actually kind of cross regulate the genes. So kind of similar, yeah. Okay. So yeah, you have autocatalytic reactions, which basically a particular product, it's regulating itself. So this is a good example. Gene, there's an mRNA, the protein, and the protein is regulating itself. So this is a positive feedback regulation, and these are your assumptions that the X1 is your mRNA, X2 is your protein. These are your production rates, and these are your degradation rates. If you just put it in the Hill function, so basically you do not write the whole Hill function here. You write the parameters. What is your substrate? What is your uh, parameter, and what is your n if it is a positive or a negative. So this is how the equations of both x1 and x2 will look. So x2 is your protein that is getting formed, and x1 is the mRNA, right? So you can directly use the Hill equation to talk about the production, and gamma 1 x1 is the degradation of that particular, or using up of that particular element. Same with x2, but in this case, there's no Hill equation involved because uh, it's a direct formation of like a protein from K2. It's no binding or anything. It's like that. Things like these are not involved. So this is a type of ODE that shows positive feedback. If you do a negative feedback, the only difference here would be, I think, your n. Two things will be different. Your n and theta, those are different because your parameter so anyway will be different for different equations, but your n will be different depending on the kind of binding that is happening. So the you see a negative Hill equation in this case, right? So that is there. So the difference between these two equations is just the type of Hill equation that you are using. And if you want to define steady state for positive feedback, there is no steady state. If you can imagine, so it will go on and on and on forever because it's just positively regulating itself. The more it makes the protein, the more gene expression is there, the more it makes the protein again. So it's a loop and it's going on and on. There is no stable steady state here. But in this case, you will find steady states, and
But in
I'll
biological systems, would it not reach a steady state because of degradation of the RNAs?
In real life, probably there will be other things in check as well, like how much protein is getting formed, and if that protein is, say for example, a lot of protein is getting formed and that protein is not
Yeah,
getting used up, so it will have a ubiquitination of that protein. The protein will be
right, right.
degraded off, and
Produce
those
them.
kind of things. Yeah, but here we are just assuming a simple model. Then there
Okay.
is no external factors. But yeah, in regular biological systems, there will be checks in place to not make that happen. Yeah. Yeah, so this is how your steady states will look like if you solve these equations and do dx equal to 0. This is how your steady states will look like for I think this is for your mRNA and this is for your protein. So initially, see the amount of mRNA is very high, then and initially the amount of protein is very low. Then it increases. Here is a peak for this one, and the peak of the protein comes a little bit later, assuming that like there will be a delay between formation of mRNA and formation of protein. So this actually correctly depicts what is known as homeostasis. So uh, and after a certain point of time, the mRNA degrades, not degrades, the mRNA stagnates, decreases and stagnates. Same with the protein. So it reaches a equilibrium state or a steady state, which is not the case for a positive feedback regulation where there is no steady state formed. Okay. So that equation is used up here. If you want to take this information and kind of model a gene regulatory network, this is what will become. If you it's the same thing depending on the, so this is the negative feedback loop here. So in this case you have used a negative Hill equation, and this is the positive feedback loop here. So this you have used as a positive Hill equation, and you can add a lot of things. I'll skip this slide as an example of how you can do stuff, not going into much details, but this regulation might not be very direct. It can be, so what can happen is, so for example, this gene is producing an mRNA, it's producing an enzyme. This enzyme actually helps in some sort of catabolism of a particular product, of a substrate, or like formation of a particular product, which is metabolite M, which can go and bind with a repressor protein and make it active, and then it can regulate the expression of this particular gene. So this loop might not be very direct. So directly protein be affecting gene A, that in many cases that will not be the case. There will be another one, two, three more proteins that are involved for this particular reaction. So you can have a set of uh, differential equations. You can write those and uh, solve them. And yeah, you can add other regulatory elements as well. So here they have added these two particular regulatory elements, which are tau and 1 and tau 2, which actually forms a like kind of a checkpoint in terms of the regulation key. Like if the particular substrate has reached a certain concentration, then only it will be able to regulate or something like that. So yeah, this is how we model a gene expression network. So take each of the components of the network and you write models for each of the components, and you have a set of models for all the whole component, gene regulatory network component, and then you can solve it and uh, uh, see the behavior of the system and how the concentrations of different substrates and products are changing with time. Okay, okay, then that's all I think from this side. Yeah, Hill function we discussed. So yeah, I'll. If you want to read about the Hill function, actually a lot of good stuff is written into Wikipedia page. So this is actually initially this sigmoidal curve was used for the binding of hemoglobin. and that is where from the first where Hill equation first came to place. But yeah, we use it now for a lot of other things. Anyway, so I'll quickly touch upon this, and then we'll move to some questions from previous years and stuff like that. Okay, so this is a very interesting concept there. So this is known as Waddington's landscape. I'm going a little bit out of the course, but I think this is very interesting, and you might want to like read up on it in the future as well. So, so this is actually the figure is actually a drawing of an epigenetic landscape depicting how a cell progresses from undifferentiated state to one of a number of distinct differentiated cell fates during development. So your cell starts here, it reaches here. There is a certain probability it goes on this side. There's a certain probability it goes on that side, and then it reaches this here, and it goes from here. There are certain probabilities, and so on. Right now, what it is exactly describing, if you can imagine, conversion of stem cells to specialized cells. So what it is saying is, so at time which is very near to the origin of the stem cell, and it has not fully yet differentiated, a lot of bistability is. So at this point of time, this cell can move here, or this cell can move here. So this is a bistable state. Right now, if you look it from this point of view, so if you're looking at from the starting or the ending point of view, so if you're looking from here or you're looking from here, so this point is a bistable state in the fact that a cell can move to two different paths from here. So if it's a stem cell, it can move to either being an epithelial cell or a mesenchymal cell. So that's a bistable state right there. So this cell is actually the ball. It falls around, and where it goes will determine its fate. So this actually is explains multistability from a biological perspective, and how multistability might be formed from a biological perspective. All the cells are coming from some sort of stem cell or some sort of undifferentiated cell, and getting differentiated to form specialized type of cells. And at each point of the differentiation, it has a choice to be a lot of it has a lot of options that it can be. So at that point of time, that cell is at a multi-stable or a bistable or whatever number of options it has. If it's a multiple options, it will be multi-stable at that point of time, because it can exhibit behavior of all those particular cell states it can be, right? So this actually is a very good this is a paper. I do not remember what paper is it, but you can just Google Waddington's landscape, and it actually tells you. It will tell you great detail in this. So this bistability and the bifurcation of from bistable to a monostable state, going through that process, that actually is influenced by a lot of stuff like external stimuli, homeotic genes, it can be epigenetic stuff. There can be a lot of things that actually determine this particular cell state and why it moves that to that particular cell state. So yeah, you can actually read about it. This is a little interesting if you are interested in this kind of things. So yeah, okay, then yeah, the rest of the stuff I had kept as examples. So this is how do you model an yeast cell. This is the actually the paper. If you want this, I don't have the writing here. So yeah, this is actually the paper, uh, integrative analysis of cell cycle control in budding yeast. So they have actually uh, like done the whole modeling on like this budding yeast, how it uh, goes from a zygote to a full-grown yeast, and how it divides again to form a zygote again, and those kind of things. So this is actually the whole network of proteins that are involved in this particular process. And these are a list of, I think there are 20, 30 differential equations that are involved in this particular process. And solving these equations can tell you a lot about the behavior of that system for this particular states. Yeah. So there were 36 ODs, 130 parameters, and 24 equations. So they solved it, and like, they predicted the behavior of how this uh, cell state changing works and everything. Okay. Okay, then we move on to the questions. I have few questions only. I think 5, 6 questions I have. We'll discuss these, and Uh, yeah. Okay, I'll keep these questions in for a minute. You can just, I think only you are there in the, no, there's another person in the meeting. So both of you can actually unmute yourself and give me the answers, and then we can move on to the next one. Sorry, somebody say something. Okay. Uh,
This is the difference between the observed and predicted states.
yep. And the last on answer is also correct. It's known as objective function, and it also always has to be minimized. So because the cost function is, as you correctly said, it's the difference between observed and predicted values. So to get the best model, you need the difference to be as low as possible. So you always want to kind of minimize this particular function. And yeah, see. Okay.
Cooperation.
Yeah, this we discussed. So yeah, if n is greater than 1, so I'll quickly go back here. N is greater than 1, it's positive binding. N is less than 1 is negative binding. And n is equal to 1, it's independent binding. So yeah, there is no positive negative involved in this. Yeah. So yeah, cooperation.
So the difference between like forward and backward Euler is
Sorry?
is it like the difference between Euler's forward and backward method?
No, so
Express.
so so I'll first tell you what's implicit means actually. So if you see the two equations, there is a fundamental difference in these two equations. So in the left one, you have x2 defined as a function of x1 and t1. But in case of the second equation, x2 is defined as a function of x1 as also a function of itself. So that is what is known as an implicit function or an implicit differential equation. So if you are defining the differential equation on the basis of itself, right? So x2 is defined on the basis of itself. So that is how a implicit function is defined. And we have not talked about Newton-Raphson methods, but Newton-Raphson method is the ideal choice of method uh, to actually solve implicit differential equations. So the answer will be that both of them are true. This is an implicit function because it is defined. Sorry. Okay, I thought someone said anything. Okay, so this is an implicit function because x2 is defined based on itself only. So that's an implicit function, and if it's an implicit function, Newton-Raphson method is a good way to describe it. I don't think like you need to get into the details, but yeah, it's another numerical method where you can use to solve implicit differential equations easily. Like it's a better method than Euler actually. Yeah, I don't know. Somebody said forward and backward of Euler, and it's not anything like that. So please don't be confused.
Okay. Model A is best for delay, model B is best for a peak, and model C is best for steady state because these the
Okay.
option last option.
Uh, yeah, I think that is correct. So model B is showing the peak as is given by your system, but there is a delay involved in this, so it's good at showing the peak. But the delay actually is shown by the model B, which is the red. Sorry, model A, which is the red line, which shows the delay in achieving that peak, and the steady state is this part of the function, which is given by model C. This is pretty clear, I think. If you have any questions, please ask, but I think this is very clear. So model B is showing your peak, model A is showing the delay in getting to that peak, and model C is showing the saturation for that particular. Yeah. So I hope you know what. So basically, you can assume these are box plots. So I hope you know what box plots are.
Mean and standard deviation being
Yeah, so basically what it's showing is if it's a
error
long
bars,
line like this, there's a lot of variance
variation.
associated with this particular data point. So that is what it is
For the
showing.
first ones, it lower standard deviation, and last one's
And
higher standard deviation.
yeah,
But
yeah.
in this case, because aren't you taking different standard deviation for each case because theta of I, right? So isn't it understood that it would take the standard deviation of the corresponding point?
No, so you are no, just to be clear, this standard deviation that you are defining, that's for the predicted value at that particular point. So at time t equal to say whatever this is, say assume one, at time t equal to one, you have a set of 100 values for like iteratively you have generated 100 values, but 100 values are actually have a lot of variance. So these values are not close to each other. So this particular data point, for this particular point at time, the, the iterative model that you have run has given you a set of values, but that values has a lot of variances associated with it. So
Okay.
depending on so your model will work on a few points better, and in a few points it will not work as well. So you need
Okay.
to understand the drawbacks of the model and use the cost function or the objective function efficiently to kind of less penalize the values that have a lot of variation within them and more penalize the values that have a lot of less penalize the values that have less variation among them. It's a more of a saturated point, but if you have a lot of variation around a particular data point, you would want to penalize more. That is the idea. Yeah. So the answer is basically lower delta for the first three data points. You want to penalize those less because those have given you a less variable less variable data. But on the right hand side, you have three data points which have given you a lot of variation. So you would want to penalize those values more in your cost function. Yeah. Right.
The data points are redundant because you can just have 2 points which signify the same line. Doesn't matter. You can just have 2 points.
Yeah, yeah, that's true. It's basically at you see all the data points are defined at the steady state line. So yeah, it's basically redundant. So you need more information for this. Yeah, I think that's all from my side. Yeah, I hope you uh, guys like the session. If you have any questions, you can ask. or else we'll close the session.
Thank you. It was a good overview.
Okay, thank you.
Thank you so much.
Okay, thank you. See you next week, same time. Bye bye.